In this video, we're going to take another look at how we can factor trinomials, and we're going to take a closer look at trinomials that don't necessarily have a greatest common factor and what we can do to break those down. So here we have 4 different trinomials, and these are trinomials in standard form. If you look at the terms, the degrees of each monomial goes from greatest to least. We have degree 2, degree 1, and degree 0 are constant. And the one thing that all of these trinomials have in common is that their lead coefficient is 1. So we have 1 here, we have 1, and 1. We start with these because they're a little simpler to factor than trinomials that have lead coefficients other than 1. When we go to factor these, we are going to look for factors of the last number. Because when I factor this, I'm going to write it as a sum of 2 binomials. And we're going to have 2 digits here that multiply together to give me 12. When we distribute, we're going to have x times x, and then we're going to have our x middle terms. But these 2 digits, when I multiply them together, will give me this last number. So I'm looking for factors of 12. I'm going to have my x here. Those factors need to add up to this middle number, 7. So we're going to have x plus something else, because we're going to have factor number 1 times x, and then we're also going to have factor number 2 times x. And when we add them, we're going to get our middle term. So we're going to look for a sum of 7. So I'm going to look for factors of 12 that add up to 7. And we can generate a list. We can say we have 1 and 12, those add up to 13. We have 2 and 6, those add up to 8. And we have 3 and 4, those add up to 7. And now I have the factors that I want. So we say, okay, we know that we're going to use 3 and 4 because they give us the correct product and sum. So when I go to write my factors, I'm going to have x plus 3 times x plus 4. And this is this polynomial in factored form. If I wanted to check my work, I could go ahead and multiply through. So x times x is x squared. X times 4 is 4x. 3 times x is 3x. And 3 times 4 is 12. All of that combines for x squared plus 7x plus 12, which is what we started with. But again, if we're asked to factor, our answer is going to be this factored form right here. This works when we have subtraction here as well. So in this instance, we're going to look for factors of negative 20 that add up to negative 8. So we know a couple different things are going on here. Since I end up with a negative product, I know that my factors have different signs. One is going to be positive, one is going to be negative. So I can kind of adjust this as I go to get the sum that I want, that sum of negative 8. I can start to think about factors of 20. We have negative 20 and 1. That's going to give me negative 19. We have 20 and negative 1, which gives me positive 19. It's going to be a lot of different factors, especially for a number like 20 that has so many. So something that we can do to help us out is to use our graphing calculator. I'm going to pull up my calculator here. And oh, we don't want to double it. That's too big. So we can go through, and similar to how we found perfect square factors, we're going to do the same process on the calculator. I'm going to go to y equals, and I'm looking for factors of negative 20. So I'm going to take negative 20 and divide it by x. This is going to divide negative 20 by every integer, and it's going to give me a table with all those factor pairs. So I'm going to hit second graph to go to the table. And now if I look across, I can see all these pairs of factors. So we have 1 times negative 20. That sum, like we said before, is going to give me a negative 19. We have 2 times negative 10. And that's going to give me my negative 8. So that's the pair that I want to use. So I'm going to come back over here. We have 2 and negative 10. And we add those, we get negative 8. So we know that that's correct. So we have x plus 2, because it's positive, and x minus 10, because we had our negative answer here. Go ahead and pause the video and try the bottom 2 on your own. See if you can figure out which numbers you need factors of, which numbers you need to add for your sum, and see if you can figure out what those polynomials would be in factored form. take a look and see how you did. For our first one in the bottom, we know that we want factors of positive 50, and those factors have to add up to negative 15. So at first I might be thinking, I'm positive 50, but they add up to a negative. That doesn't really work. But we do know that if we multiply two negative numbers, we get a positive product. So if both of our factors are negative, that will give us that positive 50 that we're looking for, while also summing to a negative 15. Those factors end up being negative 10 and negative 5. So in factored form, we have x minus 10 and x minus 5. In the second example, we're looking for factors of negative 45 that add up to positive 4. Just like the one directly above it, since our product is negative, that means we're going to have one positive factor and one negative factor. But this time our sum is positive, so it means the factor with the larger absolute value is the one that's going to be positive. So we end up with positive 9 and negative 5, and we have x plus 9 times x minus 5. Go ahead and try the polynomial on the left on your own. Alright, so for this polynomial we're looking for factors of negative 32 that add up to negative 8. And if I go through all my factor pairs, this one's not going to work. There's nothing here that gives me the sum of negative 8 while still adding up to negative 32. This means that this polynomial cannot be factored. And if we think about numbers that can't be written as a product of multiple factors other than one in themselves, we call those prime. So we would say that this polynomial is prime. Now, I know that in the past we've gone through these, we've shown out the table, the list of factors. The only time that you're required to do that is when you're going to say that a polynomial is prime. This is your work or your justification. This shows that you have tried every possible combination and nothing works, that you know it must be prime. So for a prime polynomial, you must show the table. Okay, that's your work for saying that something is prime. Otherwise, you don't have to show the table. So as you get more practice, for something like these questions on this page, you can just jump right to your answer. That's okay. Now, this works even if we have multiple variables. Our answer is just going to look a little different. So now instead of just looking for factors of 18, we're looking for factors of 18y squared. And we're looking for a sum of 9y. We leave that x out of it because we usually leave the x out here. Okay? So factors of 18y squared, we could have 18y and y. That gives me 19y. We could have 9y times 2y. That'll give me 11y. We could have 6y and 3y. And we add that, and that will give me the 9y. So my two factors are going to be x plus 6y and x plus 3y. So whatever's attached to the x is what we're looking for as our sum. All right. So now when we have a lead coefficient other than 1, we have a little more work that we have to do because we have to take that into account. If I were to just write two factors, when I multiply them together, I'm going to have an x and I'm going to have something else that I'm adding in here. But now instead of just getting x squared, we have to get 4x, or in this case r. So you could have 4 and 1, we could have 2 and 2, we have to figure out what goes with each of those. So it's a little more complex than what we were doing in the past. But we're still going to use this idea of factors of a certain product that add up to a certain sum. The way now that I'm going to find that product is by taking the lead coefficient and the constant and multiplying them together. So 4 times 3 is 12. So I'm looking for factors of 12 that add up to positive 7. So if we think about that, we could have 1 and 12, that's 13. We could have 2 and 6, that's going to be 8. We have 3 and 4, that adds up to 7. That's what we want. But now we can't just jump right to our factors. So I'm going to take these two values that we've figured out. I'm going to keep my 4r squared. I'm going to keep my plus 3. But now I'm going to use those two new factors to rewrite my center term. Because we know that the sum of 3 and 4 is 7. Which means that I can take out 7r and replace it with 3r plus 4r. And I'm actually going to rearrange those for a minute that you'll see why soon. Because we know that 4r and 3r are equivalent, I can substitute those wherever I want in an expression. Now if I look at my polynomial, I have two groups of terms with common factors. So I have this term here on the left and this group on the right. If I start with the group on the left, the common factor between these two terms is 4r. When I factor 4r out, I end up with just r plus 1. If I look at the box on the right, the common factor is a positive 3. When I factor out 3, I end up with r plus 1 left over. Now if I look at that expression, I still have two terms, each with a common factor of r plus 1. So I'm going to factor out the r plus 1, and when I do that, I have 4r plus 3 left over. We check to make sure that there's no more greatest common factors, and when there aren't, we know that we've completely factored the polynomial. So we're going to try another one together before you guys move on to on your own. So again, we start by looking at our our lead coefficient times our constant. We multiply those together. So we do 6 times positive 15, we get 90. And we need factors of 90 that add up to negative 19. Since our sum is negative but our product is positive, we know that both our factors have to be negative. So we're dealing with negative 10 and negative 9. Again, I take those, I use them to split up my middle term. So my 6x squared stays the same, my positive 15 stays the same, but now I'm going to rewrite negative 19x as negative 9x minus 10x. And notice how I choose to write terms that have common factors next to the terms they share those factors with. So I put the 9x next to the 6x squared, the 10x next to the 15. You could also reverse it because we have common factors the other way. Sometimes it'll work out like that. Now I'm going to look for those GCFs. So I have a greatest common factor between these two, and I also have a greatest common factor between these two terms. Here between 6 and 9, my common factor is 3. Between x squared and x, we have an x. If we factor that out, 6x squared divided by 3x is going to be 2x. Negative 9x divided by 3x is going to be negative 3. Then we take a look over at this term. So we have a negative sign here, which usually means I'm going to be pulling out a negative term. I know in the past we talked about greatest common factor looking to pull out the positive, but here we want to pull out the negative. So for negative 10 and 15, I'm going to pull out that negative 5. You can also look at it as just dropping the minus sign down and then ignoring it and just looking at 10x and 15. So we pull out a 5 from 10x and we have 2x left over. Now we pull out the 5 of 15 and we have a 3. But there are two things to keep in mind. When I multiply this negative 5 by this 3, I need to get back to a positive 15, which means if I'm multiplying by negative 5, I have to have negative 3. The other thing to keep in mind is that I want these two factors to match so I can eventually pull them out. So if they don't match and we've gotten to this step, we know that something's wrong. So we factor out that 2x minus 3, and when we do that, we're left with 3x minus 5. We check there's no common factor between 2x and 3, nothing between 3x and 5, and we know that we have our final factored form. Sometimes when we have a trinomial, there's a greatest common factor hiding in there. It doesn't matter whether you factor it out at the beginning or at the end, you're still going to get the same answer. But just keep in mind that in order for your polynomial to be completely factored, you need to eventually pull out that GCF. I'm going to ask you to pause the video, try one of these, and then compare your work to the second. Alright, so if we take a look at the example on the left, if that's the one that you tried where we do the GCF last. We have 8 times negative 6, so we have factors of negative 48 that add up to positive 8. So we use negative 4 and 12 to split our middle term. We find the GCF of each half, And when we do that, we end up with 2m minus 1 times 4m plus 6. 2m minus 1, those are two relatively prime terms. There's nothing we can do there, so we know we're good. But if we look at 4m plus 6, between 4 and 6, I have a common factor of 2. So we have to factor that out here, and we're left with 2m plus 3. Now we know that when we're multiplying, the order of our terms doesn't matter. So it doesn't matter the order in which you put these factors. The only thing we will worry about is always putting just a numerical factor out in front. We'll never sandwich it in between two parenthetical factors. If we look at the example where we factor out the GCF first, we immediately look at this and we notice that we have a GCF of 3 that is common to all of the terms. So we pull that out, we multiply our 4 and our 2 together to get 8. So we're looking for factors of 8 that add up to -9. Now when I go to start factoring, I have to remember that I pulled that 3 out because we don't want to leave it out of our answer. So we have 3 times, and then we use the -8 and the -1 to split our middle term. Now this one's a little tricky because we have some things to watch out for. In our first two pieces, the common factor is 4x, so that works no problem. Then we bring down our minus sign. And if we look at x and 2, the common factor there is just 1. That's it. So we have our parentheses. 1 times x is x. Great. Then we have this negative outside, and we need to get back to plus 2. So we put a minus 2 here. Then when we go to factor everything out, the common factor between each half here is x minus 2. So we factor out our x minus 2, and in the first term that gives us 4x. But then since the only thing here is the x minus 2, and we divide that by x minus 2, we're just going to get a 1. So our fully factored form is 3 times 4x minus 1 times x minus 2. Now, one of the reasons we do this is because it creates simpler equations that we can use to solve for the value of our variable. The zero product property is exactly what its name tells you. That is, that if a product is equal to 0, then one or more of the factors must be equal to 0. So if we break a polynomial down into factors, we can then very easily solve for the value that makes each of those factors 0. So if we look at this equation on the left, we want to figure out what the values of n could be. So between those two terms, I have a common factor of 4n. If I take that out, I'm left with n minus 3. And this is still all equal to 0. So now I'm going to set each factor equal to 0 and see what my possible solutions could be. So for my first factor, 4n, the number that makes that 0, is in fact 0. For my second factor, the value that makes n minus 3 0, is going to be 3. I'm going to write my solutions in set notation. So we have possible answers of 0 and 3. If you were asked to solve this question, you would need to have all of this work in order to support your answer. We start with the factored form, still set equal to 0. We show the two equations that we're solving. We show all the work down to find those solutions. Go ahead and pause the video and see if you can solve the second equation. Alright, for this one, we have a lead coefficient that's not 1, so we need to multiply. So we have 3 times positive 3, we get 9. We want factors of 9 that add up to -10. So we have -9 and -1. We use that to split up our middle term. In our first group, we have a common factor of 3n. Left behind is n minus 3. We bring down our minus sign. We have our n. Then we have to make positive 3, so we have to have a minus in here. So our two factors are n minus 3 times 3n minus 1. Since that whole thing is equal to 0, I can set each factor equal to 0 and solve, and we get values of 1/3 and 3 for n.